An excellent question might be, where do such equations arise?
Seriously?
Yes, so I'll try to shed a light with a couple of examples from the text. However, I would go back to, remember one time we did a problem with mixing tanks that were connected to each other, and that generated a system of equations. Now, you might see this more often in electrical networks where the electromotive force E of t could be something that's on some of the time and off some of the time, much like alternating current, or some of the times it's 1, some of the times it's -1. Or it could be a sawtooth or something like that. That electromotive force might not be one of the typical functions we're used to seeing. But in an electrical network as this shown, with a resistor here, a capacitor here, an inductor, where is it, here, along with an electromotive force, that's here, that's the thing that might be spastic, is described by this system of differential equations. Here it is. L, which is the inductance, times di dt, which is the change, I1 dt, which is the change in the current across here, plus the resistance times I2 is equal to the electromotive force, and R, the resistance, R times C, capacitance, times the change in I2 with respect to time, plus I2 minus I1 equals 0. So this is an exercise in chapter 3, but anyway, that's one of the places where something like this might arise. Oh, yeah? So here's another one. If you have springs coupled together, these things always seem to be like a couple extra things are going on, like the extra mixing tank or whatever. Springs coupled together where they're given an impetus and then they bounce back and forth, and we'd like to model that. And so if you can imagine a spring that's attached at a certain point, natural length A with weight m1 on it, and this one has a natural length B with weight m2 on it, and it's pulled down and let go essentially, and then it starts boinging, right? So x1 is the distance that's pulled down before it boings, and x2 maybe would be that distance. Actually, that's not true. x1 would be the position of that weight m1, and x2 the position of the weight m2, keeping in mind downward is probably positive. So if that's the case, by Newton's second law, we get the second derivative. It's forces mass times acceleration. So there's the mass, there's the acceleration, and that's negative. That's proportional to x1, and then also proportional to the difference between x2 minus x1. So the net force on mass 2 is this, and so this differential equation results. And since only a net elongation of spring B that acts on M2, the motion of the coupled system is described by the second order system with constant coefficients, and just trust me that this is what it'll work out as. So suppose we gave you some numbers for this, that K1 is 6, that's spring constant, K2 is 4, that's a spring constant, the springs A and B. Both masses start at equilibrium position and have initial velocity x prime of 0 is 1, so it's x1 is pushed down 1 unit, whatever the units may be, and x2 is pushed up 1 unit. So they have some initial velocities, and then we want to solve the system. Well, the system, which is this, right, there's the second derivative from, I guess, this one. Here's the second derivative from this one. But that system of equations becomes x double prime equals 10x1 plus 4x2. Remember the value of this and the value of this. And x2 double prime is -4 times the difference between x1 and x2. Or better written would be this, x double prime plus 10x1 minus 4x2 equals 0, x2 double prime plus 4x2 minus 4x1 equals 0, with initial condition. The initial position was 0, the initial velocity was 1 for x1, the initial position of x2 was 0, initial displacement if you want to call it that, but the initial velocity for x2 was -1. And so we can solve this using Laplace transforms, but it's going to be a long video, so I'll stop it here and we'll start it with the next video.
Oh.
We don't have much choice.